If you've ever heard of Fibonacci numbers, then it probably had something to do with rabbits. Indeed, Fibonacci himself used this sequence to model the population of rabbits following 3 simple rules. There are no rabbits to start. On the first day, there is 1 rabbit. It takes 1 day to mature, and once matured, will produce a small rabbit every day. The number of rabbits on the nth day is exactly the nth Fibonacci number, denoted a sub n. It doesn't take many days for there to be a lot of rabbits. To compute the nth Fibonacci number, we can repeatedly add together pairs of adjacent Fibonacci numbers, a sub I and a sub I plus 1, until we reach an. This requires about n additions. But we can compute it faster, using linear algebra. Take the definition of the sequence and the identity. Write the system of linear equations as a matrix vector product. Let V0 be the vector representing the number of rabbits on the first and 0th day. Let F be the matrix which represents coefficients of the linear system. In order to compute a sub n plus 1 and an, multiply F by V sub n minus 1, like this. Now, approximately how many multiplications do we need? Oh, that's not good. That's no better than standard computations. We need to do more. Let's consider the computation again. To get V sub n, we multiplied the matrix F by the vector V sub n minus 1. But V sub n minus 1 is itself the result of multiplying F by a vector, namely V sub n minus 2. If we unravel the product, we see that V sub n is exactly the result of multiplying V0 by F n times. How is this any better if we still have to multiply F n times? Because computing F to the power n takes far fewer than n multiplications. Before we deal with matrices, let's think about how we might quickly exponentiate a number, say 5. As with matrices, 5 to the n can be computed by multiplying 5 by itself n times, but here too we can do better. First, we need to talk about binary representations. Consider a number in standard or decimal notation. Each digit represents the number of powers of 10 which compose it. There are 10 different symbols representing the different multiples of the powers of 10, so this is the base 10 representation of a number. We'll denote decimals like this, or as usual. What if we had fewer symbols? If we only had a symbol, say 1, then the only thing we can do to represent a number is to repeat 1 that number of times, like a tally. This is unary notation. Notice that the same number is a lot more compact in decimal than unary. To represent the number n in unary, we need n characters, while we would only need about log base 10 of n in decimal. What if we wanted our number both compact and frugal in its use of different symbols? We could use binary or base 2 notation. Here, each digit represents the number of powers of 2. The number n in binary has about log base 2 of n characters, which is more than log base 10 of n, but substantially less than n. Let's try to multiply 5 to the n quickly again. The standard process for multiplying 5 by itself n times is as though we were writing the exponent in unary. So let's try to write it in binary instead. Let n be, in binary notation, n sub k minus 1 down to n sub 0, where n sub I is either 0 or 1. If we ignore the n sub i's for a moment, we see that there are about log base 2 of n terms we need to multiply together, if we can compute each term quickly. Luckily, we can! Since we are representing the exponents in binary, each term is a square of the one before. In order to compute 5 to the n, we multiply together those terms where n sub I is equal to 1. Finally, back to matrices. Do exactly what we did when exponentiating numbers. Write n in binary and compute the power of 2 multiples of f up to f to the 2 to the k minus 1. Then multiply together those f to the 2i where n sub I is equal to 1. Again, we perform at most as many multiplications as there are characters in the binary representation of n, or approximately log base 2 of n multiplications. Once we have f to the n, it remains to multiply by the starting condition v0 to get the nth term of the Fibonacci sequence. Let's try it out by computing a sub 50, or the 50th Fibonacci number. Yeah, that's too many rabbits.